Good afternoon. During the last lecture, I introduced the definition of parallel transport. This is a map defined on the tangent space at the point gamma A to the surface S with values to the tangent space at the point gamma B at the surface S, which send a vector W0 in T gamma AS to the value at T equals B of the parallel vector field along gamma, whose value at t equal a equals W0. I want to introduce two more definitions. Definition of holonomy. So if gamma is closed, that is, we have gamma A equal gamma B equal P, then P gamma, which is a map from TPS to TPS, is also called the holonomy around gamma. And the last definition is a definition of angle displacement. Three, if the surface S is oriented and gamma has a unit speed, then the angle displacement along gamma is given by delta theta equal theta B minus theta A, where theta denotes an angle function of gamma. Now I want to present a proposition which shows that the holonomy and the angle displacement are related. So if S is an oriented regular surface and gamma defined on AB with values in S is a unit speed closed curve, then the holonomy is equal to a clockwise rotation of T gamma A S by delta theta, where delta theta is the angle displacement presented here. The proof is very easy and I will skip it. What I want to do is to show what happens if we consider two special cases. So what happens if S is R2? If S is R2, we know that parallel a vector field along a curve is parallel if and only if it's constant. So if this is the trace of your curve gamma, and for example this is a gamma A equal gamma B equal P, and this is a vector field, a vector W0, then a vector field along this loop, this closed curve which is parallel, is given by a constant vector field. Constant means that the vector does not change its direction nor length. So this means that the map P gamma from TPS T into TPS, the holonomy, is the identity. Because the vector field marked with the yellow color is a constant vector field, which at t equal a takes a value W0 and consequently takes the same value at t equal b. And this says that delta theta is 0, which is something you can also get from the picture. There is no rotation of the vector field along the curve, so the angle displacement is 0. The situation is completely different if we work on the sphere S2. And here we consider gamma to be a unit speed parametrization of the latitudinal curve in S2, that is a curve for which phi is a constant, where phi is one of the two angles which we use for parametrizing the sphere. It is possible to prove that the geodesic curvature of gamma kg, this is equal to cotangent of phi 0 and the length is equal to 2 pi sinus of phi 0. Maybe it's a good idea to make a picture. So let's assume that this is a sphere of radius 1. Then if this is the vertical z-axis and this is the origin, then a curve with a latitudinal curve in S2 looks like this, where phi 0 is this angle. Let's use another color. So this is a latitudinal curve phi equal phi 0. What is the value of the angle displacement? It is given by theta b minus theta a, and this can be written as the integral from 0 to L of theta prime s ds. But what is the relation between the derivative of the angle function and the geodesic curvature? They are the same. So this is the integral from 0 to L of kgs ds. The value of this integral is given by L times kg, that is 2 pi cosinus of phi 0. So this means that the holonomy around latitudinal curve is the rotation in the tangent space, let's say of the tangent space, by 2 pi cosinus of phi 0. Let's try to make a better picture showing this phenomenon. So I will try to copy the figure 5.16. I hope to succeed. So suppose that this is my unit sphere. And let's consider the latitudinal curve corresponding to a value of phi 0 equal to 20 degrees. To this value of phi 0 corresponds a delta theta of 338 degrees. And if you try to make a picture, you get the following. Suppose that you start from the point P equal gamma A equal gamma B, with this vector, and then you take a parallel vector field along this curve, after one turn along this curve, you get that the value at B of W, where W is the parallel vector field, such that WA is W0, where W0 is this vector here, is rotated with respect to W0 by this angle, which is exactly 338 degrees. You can change the value of phi 0, and you can make you can consider other curves on the sphere S2, and you can try to make a picture. For example, if you take phi 0 equal 90 degrees, this means that you are considering the equator, this curve here. Then delta theta, this is 0. Why? Because the equator is a geodesic, and for a geodesic, kg is 0. This implies that theta prime is 0. This implies that theta is constant, which implies delta theta equals 0. If you try to make a picture in this case, you will get that if W0 is this vector here, then a parallel vector field which for t equal A coincide with W0 is this one. So there is no rotation of the vector field along the loop with respect to W0. Okay, now let's change topic and let's talk about geodesics in local coordinates. Let's recall the following facts. Suppose that S is an oriented regular surface with orientation n, and let sigma be a surface patch which is compatible with n. And then we already know how the first and second fundamental forms look like. We have F1 equal E du square plus 2F du dv plus G dv square, and F2 given by E du square plus 2F du dv plus G dv square. We defined E, F, and G as the inner product of these second derivatives of sigma and n. In other terms, they are the normal components of sigma UU, sigma UV, sigma VV. What about the tangential component? In other terms, what can we do with the inner products of sigma UU and sigma U, sigma UV with sigma U, sigma VV and sigma U, etc. The idea is that since sigma U, sigma V, and are formal bases, then we can try to write, for example, sigma UU is a linear combination of sigma U, sigma V, sigma N, using this kind of inner product and this inner product here. We can then give the definition 5.50. The Christoffel symbols gamma I, j, k from U into R, where U is the domain of the surface patch sigma for I, j, k in 1, 2, are defined such that the following identities hold on U. The first one says that sigma U, sigma UU can be written as a linear combination of sigma U, sigma V, and N using as coefficients the function gamma 1, 1, 1, the function gamma 1, 1, 2, and the function E. Similarly, sigma UV, this is gamma 1 to 1 sigma U plus gamma 1 to 2 sigma V plus F n. Sigma VU is equal to gamma 211 sigma U plus gamma 212 sigma V plus Fn. And the last one is sigma VV equal to gamma 221 sigma U plus gamma 222 sigma V plus Gn. I want to make two remarks. The first one is apparently there are 8 Christoffel symbols, but they are only 6. Why? Because sigma UV equals sigma VU. So this implies that gamma 211 is equal to gamma 121 and gamma 122 is equal to gamma 212. In other terms, this function is equal to this function, and this function is equal to this function. So this implies there are only 6 different Christoffel symbols. Second remark is about how to remember these formulas. You have to associate to the index 1 the variable u, and to the index 2 the variable v. So what is the reason why here you have a pair of 1? The reason is that you are considering the second derivative of sigma with respect to u. So this explains why you have a pair of 1 here and a pair of 1s here. The reason why you have a 1 here is that you are considering the derivative of u here, the derivative of sigma with respect to u, and the reason why there is a 2 here is that you are considering the derivative of sigma with respect to v. Similarly, you can get why I am using the index ijk in the other equations. Finally, I want to give an interpretation of the tangential part of these derivatives. I mean this part here. In terms of covariant derivative, let's observe what do we have on the left hand side of these equations. We have, for example, sigma uu, and this can be written as sigma u derived with respect to u. This is clearly the tangential part of this derivative here. But we introduce the definition of covariant derivative as the projection onto the tangent space of a derivative. Now, since this is a linear combination of sigma u and sigma v, this is exactly the projection on the tangent space of sigma u. So this coincides with du sigma u, and I can write this formula. Similarly, the tangential part of sigma uv is the covariant derivative of sigma u with respect to v. And so on. So I have d u sigma v equal to d v sigma u equal to gamma 1 to 1 sigma u. Let's write let's write this way: gamma 1 to 2 sigma v, but also gamma 2 1 1 sigma u plus gamma 2 1 2 sigma v. So I got the fact that this is equal to this one from the second equation. This is equal to this one from the third equation, but they are equal because gamma 1, 2, 1 and gamma 2, 1, 1 are the same. And gamma 1, 2, 2 is equal to gamma 2, 1, 2. And from the last equation, I get that d dv sigma v is a gamma 2, 2, 1 sigma u plus gamma 2, 2, 2 sigma v. Now I present a lemma which explains how to express the covariant derivative of an arbitrary vector field along a curve in terms of Christoffel symbols. So we have lemma 5.51, covariant derivatives let's write derivative in local coordinates. So we have an arbitrary curve in V containing S, where V is the image of the surface patch sigma we used before. And we suppose that this curve can be expressed as gamma t equals sigma of ut vt for some smooth functions u v defined on I with value in R. Then if W is an arbitrary vector field along gamma, that is Wt is equal to AT sigma u ut vt plus b of t sigma v ut vt for some smooth functions A, B defined on R, defined on I with values in R. Then I have the following formula. the covariant derivative dw dt, this is given by a prime plus a u prime gamma 1 plus a v prime plus b u prime gamma 1 plus b v prime gamma 2 sigma u plus b prime plus a u prime gamma 2 plus a v prime plus b u prime gamma 2 plus b v prime gamma 2 sigma v. On I. Unfortunately, I have to erase. Maybe let's start writing something here. In particular, W is parallel if and only if the coefficients of sigma u and sigma v in star, where star is this formula, are both 0. The second part of this lemma is immediate. Why? Because we know that a vector field is parallel if its covariant derivative is 0. This covariant derivative is a linear combination of sigma u and sigma v. So this covariant derivative will be 0 if these coefficients 1 and 2 will be 0. If you want to prove this formula, you start from this expression. This is the generic expression of a vector field along gamma. You compute dw dt using the chain rule, and to project onto the tangent space, that is, take only the components which are parallel to sigma u and sigma v, and then use the definitions of Christoffel symbols I gave before. I prefer to omit the detail of this proof. Sorry, what it is interesting is lem 5.52 geodesic equations, which says that the regular curve gamma t equals sigma ut vt in V is a geodesic if and only if u second plus u prime square gamma 111 plus 2u prime v prime gamma 121 plus v prime square gamma 221 equals 0, and v second plus v prime, u prime square gamma 112 plus 2u prime v prime gamma 122 plus v prime square gamma 222 equals 0. The proof of these formulas is very easy. Gamma is a geodesic if and only if gamma prime is a parallel. Then we can use lemma 5.51, which is the previous one, with W equal gamma prime. If you do this, what you are doing is to replace the function a with the function u prime t and the function v with the function v prime t. Why? Because if gamma t is a sigma ut vt, then gamma prime is a u prime t sigma u ut vt plus v prime t sigma u sigma v ut vt. And now if you compare this expression with the expression of W, you get that u prime replaces A and v prime of t replaces B. So these are the equations that you have to solve if you want to find the geodesics of a surface. Maybe some of you have studied the theory of systems of differential equations, and you may know that the equations I wrote here can be solved uniquely for ut vt once that we know the values ut0, vt0, u prime t0, v prime t0 with t0 in I. So if you know the values of u, v, u prime, v prime at just one point, it's possible to prove that this system of equations has a unique solution defined in a neighborhood of t0. Okay, then the next result I want to present is a proposition proved by Gauss which says that the Christoffel symbols can be expressed uniquely in terms of E, F, G and their derivatives. Precisely we have if we set alpha to be the function 2 times E g minus f squared, then we have the following formulas. A, alpha gamma 1 1, this is g e u minus 2f f u plus f e v, alpha gamma 1 1 2, this is 2 e f u minus e v minus f u. B, alpha gamma 1 to 1, This is GEV minus FGU alpha gamma 1 2 2. This is E GU minus FEV. And it's not finished. C alpha gamma 2 2 1. This is 2GFV minus GGU minus FGV. And the last one is alpha gamma 2 2 2 equal to EGV minus 2FV plus FGU. Let's see how to prove these formulas, at least the idea. The idea of the proof is to express the inner product of 1 of sigma UU, sigma UV, sigma VV with 1 of sigma U, sigma V in two ways. For example, unfortunately I have two ways. For example, how to prove the equations at the point A. You start from sigma UU multiplied by sigma U. This can be written as the derivative with respect to U of sigma U divided by 2, that is 1/2 EU, because this is E, but also as gamma 1 1 1 E sigma U plus gamma 1 1 2 sigma U sigma V. And why? Because you have a formula for sigma UU in terms of the Christoffel symbols. If you multiply that formula by sigma U, you get only two terms. The first one is gamma 1 1 sigma U plus second gamma 1 2 sigma U sigma V, and the last term involving n disappear because n is orthogonal to sigma U and sigma V. But this is E and this is F, so we got gamma 1 1 1 E plus gamma 1 1 2 F equal 1/2 EU. Using the inner product of sigma U with sigma V, you can prove that gamma 1 1 1 F plus gamma 112G. This is equal to Fu minus 1 half EV. And you can solve now the system formed by these two equations, and you will get the equations at part A of the statement. If you consider the inner products of sigma uv and sigma vv with sigma u and sigma v, you will be able to prove the equations at part B and C of the statement. Let me check how much time I have. Okay, 15 minutes. The next proposition I want to prove is a proposition 5.54, equations of compatibility also this proposition has been proved by Gauss, and it says that there exists a relation involving the functions capital E, capital F, capital G, E, F, and G. Precisely, we have that F times K, this is gamma 1 to 1 U minus gamma 111 V plus gamma 122 gamma 121 minus gamma 112 gamma 221. As you see, they look complicated. In total, there are six equations. I copied only the first three because if you want to get the last three equations, precisely 2u, 2v, 2n, what you have to do is to replace u with v and vice versa, 1 with 2 and vice versa, and capital E with capital G and vice versa, and small e with G and vice versa. Let's see how to prove these formulas, at least the idea. Fortunately, I have to erase something. The idea of the proof is the following. Consider the identities sigma u v equal to sigma u v u, and sigma v v u equal to sigma u v v. Precisely, I will use the first identity for proving these three equations, and the second can be used for proving 2u, 2v, 2n. Okay, let's use Christoffel symbols, and if we do this, then the left hand side is equal to gamma 111 sigma u plus gamma 112 sigma v plus en differentiated with respect to v equal to gamma 121 sigma u plus gamma 122 sigma v plus fn differentiated with respect to u. Then we have to expand these expressions. So, for example, the left-hand side becomes gamma 111 v sigma u plus gamma 111 sigma uv plus gamma 112 v sigma v plus gamma 112 sigma VV, it's not finished yet, plus EVN plus ENV. Of course, I use chain rule. Now the next step is use again the Christopher symbols. For expanding this term in terms of gamma 1, 2, 1 sigma u plus gamma 1, 2, 2 sigma v plus Fn and sigma vv equal gamma 2, 2, 1 sigma u plus gamma 2, 2, 2 sigma v plus gn. So you replace these two formulas here, and it's not finished yet. We need a formula for NV. But we know how to write NV, because NV is minus W sigma V. And in the past, we have seen that if we choose the basis sigma u sigma v, then W of sigma v can be written as W12 sigma u plus W22 sigma v, where W12 is Fg minus Gf divided by Eg minus F squared. W22 equal Ge minus Ff divided by Eg minus F squared. So all this work is only for expanding sigma UUV. You have to do a similar work for sigma UVU, and then you have to equate the resulting coefficients of sigma u, sigma v, and n. And if you do this, you will prove one u, one v, and one n. As I told you before, if you want to prove 2u, 2v, 2n, just make the following changes. And you will get these three equations from the first three. Okay, now we are ready to give a proof of Gauss egregium theorem. We already presented this theorem. Essentially, using these one of these four equations, it's possible to prove that if we use a proposition 5.53, which provides the expressions of the Christoffel symbols into any of any one of these four equations. Then it's possible to write k as a complicated function where k is the Gauss curvature, of course, of E, F, G, EU, FU, EV, FV, and so on. Which says that k can be expressed only in terms of the coefficients of the first fundamental form and their derivative. Sorry, I made a typo. That is, k is intrinsic I would like to mention a corollary of this result. I mean the formula which expresses k as a function of capital E, capital F, capital G and their derivatives. In a special case, if E is equal to 1 and F is equal to 0, then K is a very simple formula This result is interesting because this generalizes the formula k equal minus square root of g r over square root of g that we saw when we worked with the normal polar coordinates. So this theorem says that this result says that a similar formula holds true if we have a surface patch for which E is equal to 1 and F is equal to 0. The last result I want to present is the proposition 5.56, which is about the measure of the failure of the formula ddu ddv minus equal to d dv d du. Precisely, we have that if W is a tangent vector field, on a surface S, then we have that d du d dv of W minus, sorry, this is a V, this is a U, minus d du d dv W, this is equal to K multiplied by the area distortion times R90 W. So this formula says that in general it is not true that these two pairs of derivatives are the same. Since the proof is a bit long, I prefer to stop here and to present it next time. Thank you for your attention.